So let's get started. So yesterday we have actually defined the basic setup of mechanism design, and in particular we were after certain desirable properties. The first desirable property was naturally the truth telling, because in mechanism design we do not know what are the private information of the agents. We want to design a system or a protocol such that it is the best response for them. So in this case it is a dominant strategy for them to tell their types truthfully. Then the second objective was to achieve Pareto optimality, which we have shown that it is equivalent to allocative efficiency. So Pareto optimality, just to recap, it's an outcome where you cannot have any other outcome which can be better, weakly better for everyone and strictly better for at least one person. So if that is the case, then we are sort of at a Pareto frontier. So we cannot do everybody better off, and we have seen that that is equivalent to allocative efficiency in the case of mechanism design with money. And we also discussed about individual rationality, which is the participation constraint, that if people do not see the reason why, if they see that there could be a situation where they can get negative utility, then they will not participate. So this is to essentially rule out that possibility that no matter whatever is the situation, whatever is the type, they will always get non-negative utilities. So yesterday we also asked this question that of course this is a very desirable property. I mean we cannot proceed without this, and this participation is also very desirable property. But what about this Pareto optimality or allocative efficiency? Why are we doing it? Yes, I mean allocative efficiency in some, so in the utilitarian objective where you are trying to maximize the sum of the valuation, utilitarian. So the sum of the valuation is going to be maximized. Yes, this makes sense. But from a seller's point of view or auctioneer's point of view, you can also think of maximizing the revenue earned by the auctioneer is one of the desirable goal, and which is definitely a very reasonable goal. So today we are going to talk about that revenue maximization objective, and maximization. So we will see that this comes at the cost of allocative efficiency. So we will no longer be interested in satisfying 2 today, rather we will be after maximizing the revenue. So even if it is not efficiently using the resource, I do not care. As a seller, I always want to maximize my revenue. It is a different goal. Okay, so let us get started. So this question we are going to ask only for a single indivisible item. So we were using this running example of selling one painting or one object, and the thing that we will discuss only apply to exactly one item. So imagine that there is only one painting to be sold. I want to sell it in the way that my earned revenue is the maximum. So notation becomes a little simplified, and the difference with yesterday's discussion is that yesterday we were mostly looking at deterministic mechanisms. Mechanism. I will define the randomized version. So deterministic mechanism, recall that we always had, so for single object allocation, we had this vector of a1 to an, and exactly one of them, each of this a1 to an, each of these things can take binary values 0 or 1, that is either you give the entire item to that agent or do not give at all. But there could be a kind of a randomization policy that where I can probabilistically say that, let us say with 70% probability I give it to agent 1, 30% probability I give it to agent 2. So those are the things that we are going to look at. So randomized mechanism, it essentially increases the class of mechanisms. Of course, deterministic is a special case of that, but we want to see that what we can say about such randomized mechanisms. So the setup is clear, right? So we want to maximize the revenue by selling one object, and therefore, what we have now is, let us say every agent has some type set. So, think about this as the capital theta I. For this purpose, for today's lecture, I will always use this T I as the type, small t I as the type of an agent, which will be a real number, and capital T I as the set of all types. You can see it here. Yeah.
Multiple object option be for example.
So it's it will be a combination, right? So we also discussed that. So if you have, so you will also have to define what is a bundle in that case. Here there is no bundle, either you get that object, you do not get that object. So that's why you have only one type in your thing, but there to define the type, I will have to define the valuation function, which is defining the value for every bundle of the object, all possible subsets of the object. Empty set is 0, but just the single item A is valued something, single item B is valued something else. The combination of A and B together in the bundle is different. So yeah, so that's more complicated. So this is much simpler thing. Okay, so that's the type set, and small t I is the type. So it's essentially the same as the value of that agent if she wins that object. Now allocation. Now unlike last time, so recall that we had this A, so each of those components, so A is still a vector, but earlier we had only 0 or 1. Now we are allowing for the interval between 0 and 1. So it can be any real number, which is saying that with what probability I am allocating that object to them. So this is the setup of randomized allocation. The set of all allocations now is we are just going to use very similar notation, delta of A, which is the simplex of all these allocations, and with the condition that the sum of this. So you see that there is I 0, that means A 0 is the probability that the item is not sold, and everything else is like the allocation, the probability of allocation to that particular agent. Okay. Now the allocation rule has to take these numbers, each of these numbers from each of these agents, like before, and it will map it to an allocation. So such kind of an allocation, which is just giving a vector of probabilities of allocation to different agents. Okay. So it may also have some probabilities for not selling the object. And valuation, as before, we are following the same notation. You have this allocation here and also the type, which is the agent, how much it values that object. So the valuation is already in an expected form, because I do not know deterministically whether I will get it or not. So beforehand, before the mechanism starts, I can only evaluate that what is the probability that I will get that object. So if it is, so if the mechanism decides that AI is my probability of getting that object, then my valuation is just AI times TI. It's also called the product form, depending on which textbook you are looking at. Okay, so therefore, so this F you can think of, F is mapping it to some element in delta of A, and it's a vector, n length vector, actually n plus 1 length vector I should have written, because I am also including 0 here. So that length vector, where F I means that this ith agent, the probability with which ith agent wins that object. Okay. Yeah, so in particular F 0 is the probability that this item is not sold. Okay. So I will also need a few definitions, but this will be very self-explanatory. So in some sense, this is when we are looking at agent I. So T minus I 2 means if I remove agent I, which one is the second, which one is the best among the remaining number of agents. So so the 2 is coming because imagine I was the winner. So coming from the second prize auction, so I was the winner, then this would have been the second highest bid, right? So that's, yeah, 2 you might ignore, it might not be needed, but T minus I 2 is the second highest bid excluding agent I. Okay, so the highest bid excluding agent I. Now, agent I will win if Vi is larger than that and lose this, and in a tie breaking rule, if there is a tie, then you can decide in whichever way you want. It could be even randomized allocation at that point. So, this is so I am just trying to phrase the in my setting this second prize auction. So, this was the rule for the second prize auction. You are always giving the item to the agent who values or reports the highest value, and yeah. So, in this case you will definitely win, in this case you will definitely lose, and you can do anything in between if they are equal. And payment was also very simple. If that agent does not win, then his valuation is 0, and if he wins, then the difference is his utility. So, we will develop all our discussions keeping second prize auction in mind, because second prize auction is something that we know satisfies all these properties, right, all these first 3 properties, and we will see that and we also know that second prize auction is truthful, satisfies the first property. So, therefore, we want to see what are the structures. We will make some structural guarantees or structural characterization of the truthful mechanisms. That is the first objective for us. So, we see that if we plot the utility function, just plot this thing with respect to the valuation, and assuming that everybody else's types are fixed, right. So, in that case, I know that until the point of t minus I 2, the utility is 0 because it does not win that object, and from then onwards it is linearly increasing, the slope is 45 degrees, right. Now, correspondingly you will also look at what is the allocation, right. So, you see that the allocation is having a jump. I just want you to observe that until this point, this allocation, the value of the allocation is exactly equal to the slope of this function, of this utility function, and after that the slope is essentially the allocation probability. So, this is just an observation, but we will see that this is not a coincidence, it will actually happen, it has to be of this form. Right. So, these are the 2 things. Do you see anything more, any other observations that you can make about these 2 functions, particularly the utility function? The shape of the utility function, can you make any comment on that shape?
Utility is continuously increasing, but we had said that yesterday that if we say above our revenue, then there is no increase in utility as such.
So it's linear.
Make any remark about revenue, I think, yesterday?
It's linear.
Okay, so in this case linear. Okay, so that's one observation. Anything else? Convexity, concavity, what kind of function is this? This is a convex function, right? I mean, so if you connect any 2 points, draw a chord that will always lie above this curve. So, at least in this particular example for the second prize auction, we see that the utility is convex, and wherever we can, so this is not differentiable here, and we have just seen that in that case we can put any number between 0 and 1, and whenever the derivative exists, it is exactly the same as the allocation, right. So, these are the 2 things that maybe you just keep in mind. We will reconnect these things when we are done our characterization. So, the first observation is this utility is convex, and whenever differentiable, its derivative coincides with the allocation probability. So, these are the 2 observations. Yeah, I mean, I do not think, is there anyone who does not know a convex function? This is a formal definition. So, if you just pick a function, so we call a function g. So, in all our discussions, we will always take an interval, and the function will map to a real number. So, in that interval I, if you pick any 2 arbitrary points x and y and calculate, I think I have a, no, okay. So, I do not have a picture here. but maybe I can just draw it. So, so a function which let us say this is g, and I have its domain as x, and I have this point x and another point y. Find the corresponding values gx and g of y, and take any convex combination of these 2 points. So, that is what I am doing on the left hand side. So, let us say I am taking lambda to be, let us say 0.5. So, I am taking a point which is connecting these 2 points exactly at the center. That point will be larger than if I look at the corresponding lambda x plus 1 minus lambda of y and evaluate the function there. So, which is this value here, right. So, this is the property of a convex function. It is true for any lambda between 0 and 1. Okay. Now, in order to develop the theory that what is the structure of dominant strategy incentive compatible mechanisms. So, here we are actually trying to get to a necessary condition. So, earlier we saw that if we want to satisfy certain properties, somehow magically we came up with this VCG mechanism or the Groves mechanism, and we showed that that satisfies DSIC property. Here we are asking the reverse question, that if it is DSIC, what are the necessary things that should be satisfied, and if they are also sufficient or not. Right. So, this is going in the reverse direction, starting from DSIC going to the structure of the mechanism. So, in order to do that, because everything here is on real numbers and we will be doing this real analysis type of stuff. So, something related to convex analysis will be useful. So, I will not go into the details of those proofs of those results, but I will just state and possibly give some intuition on one dimensional functions why this is true. Okay. So, the first thing that one can see, that convex functions are continuous in the interior of this domain. So, for instance, if I have so I cannot have a point where I have, let us say in this function I have a jump, right. So, and then this kind of a thing, this is not possible, right. So, you have some point, then you can draw a chord between these two things and you have some points which are lying below the function. But it is possible to have, so suppose my function is defined only between, let us say 0 to 1, I go as close as possible to 1, but then I have a jump, that is still fine. So, it is a open set up to, I mean this is on the open 0 to 1, it has this convex nature. It can be actually open on 0 as well, there also you can have a jump above, but it cannot have any jump inside. So, in the interior of its domain, the function will not have any discontinuity. So, this is one thing. The other thing is that the convex functions are differentiable almost everywhere. So, what does this almost everywhere mean? That if I have this non-differentiability, so which we saw in the previous case, right. So, for the utility function, we said that it is a convex function. So, let us say I have a function which has this kind of a structure. This is still convex, but this is not differentiable at these 2 points. So, what it is saying that you can only have countable number of such non-differentiable points, you cannot have an interval of non-differentiable points, uncountably many points where it is non-differentiable. So, we will use this fact very much to say that okay, I can come arbitrarily, because these are countable, there are uncountably many points around it. So, I can define a limit towards it. So, this is something that we should recall, remember. Okay. So, all right. So, few more things. So, we are going to define, I mean we know that it is only non-differentiable at countably many points. In fact, it is differentiable everywhere. So, wherever it is differentiable, we are just going to use the g prime x, the standard derivative. Now, the following definition, which many of you may have seen somewhere else. So, this is called the subgradient idea. Okay. So, before I give the mathematical definition, let us look at this picture. So, suppose I So let's focus on this point where it is not differentiable, right? And what we are going to say is that suppose I try to find a line which can support this entire thing, the entire function from below, right? So I can have a slope where if I pick any other point, let's say I am looking at this point x, I am picking any point z1 and calculate this quantity, which is the value of g at this point x plus the slope of this function times this difference. So essentially I am trying to reach to that point. This point will always lie below the value of the function, value of the convex function at that new point z1. Right? So similarly, if you have the other direction, this z1 minus x, now it will be negative. So even if you have the plus, the slope is positive in this case. So you will come down below. So below gx, this will also be below this one. Right? So so what will be this slope? Let's say if I pick my x to be somewhere here. Okay, so in this blue point, what will be the so let's say at this point x, the red x, is this x, the slope x star, unique? So what other things can we have? I can have any other arbitrary slope, right? So all of those will actually satisfy this condition. What about this point at blue x? Can I have multiple x stars? So you will and what will that x star be if cannot have multiple x star? It will be exactly equal to the derivative, right? So subgradient is essentially generalizing this idea of derivative, because wherever the derivative exists, the subgradient will be exactly equal to the derivative. You can actually think about this in higher dimensions as well. That is why the name subgradient. If it is only one dimensional, you can just say it is subderivative. But anyway, the idea is that where it is not differentiable, you can have multiple possibilities. Where you have exactly one derivative, the derivative exists, then it coincides with that. Okay, so this subgradient idea will also be useful, as we will see very soon. The question that quite naturally comes is whether it will always exist. If I give you any arbitrary function, so at this point we are not saying anything about g, right? So g could be differentiable, non-differentiable in some places. It can be any arbitrary continuous function. So let's say I have an arbitrary continuous function. Okay. At every point, can I define a subgradient? Okay, so let's say this point here is there a subgradient? Okay, so yeah, so the subgradient will be, I mean, because we have assumed we have taken a function which is also having a derivative, so you can just have a slope and that will be exactly equal to that. What about this point? Cannot satisfy this condition, right? Because the condition is saying that you take any line, so starting from that line on this direction or that direction, the entire curve should be above that, right? So what does it, so where can we actually satisfy, where can we always define a subgradient? For convex functions, right? So we cannot define it for non-convex functions, regardless of whether they are differentiable or not. So this is an important thing, that we can only define it, it exists and we will see a result. It always exists when you have convex function. And whether it is unique or not, I think the uniqueness question we have already visually seen, that if the derivative exists, then it is unique. If it is not, the derivative does not exist, it is non-differentiable, then it is not unique. Okay? Yeah.
Here, it is also not unique, it is differentiable at x, the first x.
No, so if you have, yeah, it is differentiable, but
it has multiple subgradient.
so why?
Just draw a graph of y is equal to x.
Okay.
Then check at 0.
Okay. Right. Yeah. So yeah. No. No. No, so for instance, you cannot have any slope which is larger than 0, because then, yeah, I mean, of course, it is not visible here, but there will be some points, yeah, so some points which will be below that thing, right? So if it is differentiable, of course, that will have to be the same. Yeah, and that's true for any arbitrary. I mean, you have taken a convex function. For even non-convex functions, you cannot tilt that that subgradient anything different from the gradient. Yeah, good. So okay, so let's yeah. Any other questions about this? So this idea will be. You can already start seeing the connection between the utility function, allocations, etc. Right. So yeah. So just keep thinking before we get to there. So okay. So it always exists. Is it unique? The first result again is some standard results. If it is a convex function, so that is a required condition. Of course, there may exist other functions for which it will also exist, but convex function is sufficient to say that it is in the interior, it is differentiable, then G prime is the unique subgradient. So this settles the second question, that where it is unique. But if it is non-unique, then also it always exists, in particular in the points where it is non-differentiable. So let us say this I prime is the points like those. So this intervals where it is differentiable, right. I am taking out those points, I primes I am taking out from an interval. The set is already measure 0, that we have already seen, there can only be countably many such points. The set of subgradients at a point forms a convex set. So what does that mean? So yeah, remember that what was happening. So let us say I pick the subgradients at this point. I can have a point like this, I can have a subgradient like this. In fact, everything between these 2 points are all subgradients, right. So start from this slope, right. So that is, let us say, my x star 1. This is a subgradient up to this point where it is x star 2, right. So that is what I am going to define as you approach this point from the left or the right, whatever is the gradient of that function, because I know that there are only countably many such points. So I can always define this limit, limits are well defined, and that starting from that slope to the other slope, when I am approaching this point from the plus side, within this interval all the subgradients will lie for that point x, right. This is the intuition. I mean, we have not formally proved it, but you can see from x1 star to x2 star, that is the interval where all the subgradients will lie. Okay, so let me just try to summarize those previous results. So let us say if we want to define the set of all subgradients at a specific point, delta g of x. So what will be the delta g of x, let us say at this point? What size of that set will be? What will be the size? It will be a singleton, because that is just the derivative, right. So and the second lemma is saying that it will be a non-empty, but it will be an interval between this, the left slope to the right slope. Okay. Now what I am going to do is I am going to pick, so I am going to define a function, let us say phi, which is picking the point, right. So it is always taking a value. So if you give me any z, I look at its subgradient set, the subgradient set given by delta g x, and pick one such point. So for instance, if okay, so let us for simplicity assume that I had that function. So the slope was -1 here and then +1 here. So I know that up to this point, so the phi of x, if you want to plot it, this will be exactly equal to 1, sorry, -1. So yeah, so all the points. So if I just want to draw this one, okay, let me just erase this part. Suppose this is my g function and this is my phi function. So it is not unique, but you can always say that this -1, so up to this point this was -1, and then you can pick any number between -1 to +1 at this point, and then start from here as plus 1, right. Let us say I pick this one. So, this is one of the phi's, there can be multiple phi's. So, this lemma is saying, and which is very much observable from here, it will be non-decreasing function. Because it is a convex function, you know that if it was differentiable, then you exactly know that the derivative will keep on increasing. So, this function will be monotone increasing. If it is non-differentiable, you define this function which is picking some value. It could be non-continuous, but it will still have this property that it is non-decreasing. So, so few properties like this, the properties of subgradient function. Okay. So picks one value at every z, even if the subgradients can be many. Monotone non-decreasing. And the final result, I think, so I think we are in the final result. So this is equivalent to the integral form, the fundamental theorem of integral calculus, right. So if you just replace this phi function with the derivative function, this is exactly how the integral formula is defined, right. The value of the function at x minus the value of the function at y is essentially the integral of the derivative. So this is also true for subderivatives or subgradients. We will not prove it, we will just use it. All right. So I think we are, any questions about this this basics of convex analysis? Okay. So if these are all fairly intuitive, then let us get into the main result. So this is the result by Meyerson, which gives us a characterization of what is a DSIC mechanism. So first we will, before we maximize our revenue, we first have to characterize what is a DSIC function, because that is the way, that is the path that is taken. So that I first want this property and individual rationality, and in this class of mechanisms which satisfy both 1 and 3, which one maximizes revenue, right. So we need to know some sort of a better mathematical structure of characterizing or mentioning this type of a mechanism. So this is the first result. Okay. So just like we have defined monotonicity, we can also define the allocation, the non-decreasingness of an allocation function. What is it saying? That suppose at some point Si, so other players, I am not focusing on the other players are reporting some t minus i's. You have reported Si, and suppose you have not owned the object, right. So let us say the probability of winning was very small, maybe 0.2. If you increase your Si from your valuation, if your valuation increases from Si to Ti, that is whether you report it differently or your valuation intrinsically improves, then you will continue, you will at least have the same probability of winning. So it cannot happen that earlier I had a 20% probability of winning that object, now my valuation has increased and my probability of winning is now 10%. That cannot happen. So this is actually telling me that this type of allocation function, which satisfies this monotonicity property on that ith coordinate for all the players, this we are going to call as non-decreasing. This is a key word. So non-decreasing. Okay. The probability of allocation never decreases with the valuation. So notice that this is true for second prize auction, right. So imagining everybody else. So let us say I look at not the winner, somebody who had not owned the object. So their valuation, currently their valuation is 0, their allocation probability is 0. Now suppose they started increasing their valuation or started reporting higher valuations. So there will be a threshold point after which it will start winning that object, right. So that is monotone, I mean it is a step function, and that is true for all the other agents. For the winner, it is already 1, so the Fi was already 1. So it is just saying that you will continue to win if your valuation increases even further. It cannot happen that the highest bidder, his valuation increased and he suddenly stopped winning, right. Okay, so this is true for that, but so this is the property of an allocation function. Now what is Meyerson saying is that, so this is the same thing. So suppose we have again this is required. So, your type set is the interval between 0 to bi. So, therefore, your valuations can only lie between 0 to bi, any number, and the valuations are in that product form. I mean, that is the way we have said that allocation. So, this fi times their valuation or their ti is the value that they get. Now, the allocation rule and a payment rule, this is the same way we have defined it in the first slide, is DSIC if and only if two things happen. The first thing is f is non-decreasing, that is it satisfies this property that you cannot have a dip after your valuation has increased. And the second condition is that these payments are given by a very specific integral formula. You can already begin to see that the integral thing that we have done has some similarities, and we will connect that back. But yeah, so at this point I am not going to explain this. When the time comes, we will explain each of these terms. So, it is, so we can actually say, so the only thing that I can tell you here is that there is a kind of a constant function, it is like a constant of an integration, which is giving you the value of this function at 0, because that is the minimum value that this agent can get, and everything else is in terms of the allocation function, right. So, once you have fixed the allocation function and you have fixed this this constant, let us say it is 0, then the payment is already fixed. So, it is saying that you can pick any non-decreasing function, any monotone function which has this property, and then if you use this payment, then you are guaranteed to have a DSIC mechanism. And the converse is also true, that if it is a DSIC mechanism, then it must necessarily satisfy these two conditions. Okay. So, the necessary direction is more difficult, and that is why we needed all those results from convex analysis. We will see how we use it. The reverse direction, we will actually do a proof by pictures, that how given these two conditions, how we can show that this is DSIC. Okay. Any questions about this thing? So, these two conditions are equivalent to DSIC. We will also see that this individual rationality will put some condition on this constant. So, now we are actually heading towards what we actually wanted. So, we have this rather a little better structure on this DSIC mechanisms. Individual rationality will ensure some conditions on that PI. Subject to those conditions, we are going to maximize the sum of the payments. That is the whole objective. Okay, so I don't, so because we have not discussed Robert's theorem, so this part is not relevant. Let us start with the proof. Okay. So, this is the forward direction that we are starting with DSIC, and we want to show that those two conditions are satisfied, right. Okay. Now, I am going to define two different terms. So, the utility when its type is Ti, and so if its true type is Ti, then the utility is so the mechanism is fixed. So, at this point I am not going to change anything about the mechanism. So, that mechanism is fixed. So, therefore, this will be the utility, and if its utility changes, sorry, the type changes to Si, then this will be the corresponding utility, right. So, if I write down on the left hand side this utility at Ti t minus I, what is the DSIC condition? Let me go over this slowly. So, I want this Ti Fi Ti t minus I minus Pi times Ti t minus I. So, what? So, of course, this is greater than equal to, let us say I move to some, so the agent reports something else Si. So, what will be the right hand side here? Because this is DSIC, yeah. So, what should I write here? Ti Fi Si t minus I. So, that means you are just reporting it. So, therefore, you are changing the allocation, but your true type is still evaluated with respect to Ti minus Pi Si t minus I. Very good. Okay. So, I will just do a little bit of replacement, because so you see that this is how I have defined my ui ti t minus I. I want to show that this function is convex, and then several other properties get satisfied. So, I somehow on the right hand side want to bring in this ui si t minus I. Now, notice the difference, I have this si multiplier. So, you can just add that term si and subtract it out. Okay. So, I can write this as si times fi si t minus I minus pi of si t minus I, and then ti minus si times that fi of si t minus I. So, this is straightforward. So, now I have this term which is nothing but the ui of si t minus I, right, and the rest of the things. So, essentially that is what I have done. So, I have just replaced this, so that I have an inequality between ui ti t minus I and ui si t minus I, and this one. So, can someone see any similarities with whatever we have discussed so far? We had some inequalities in the definitions before, where we said that if you go from one point to another point, take the difference between those 2 points, multiply with something, it should be above that one, subgradient, right. So, how can I actually say that? So, let us say I define. So, see here everywhere. So, we are just looking at from the view of agent I. So, I can actually treat t minus I as a constant. Okay. So, I can define, let us say, some function of g of the variable as only as t. What is this? So, this is just fi of this first coordinate, the second coordinate remains fixed t minus I throughout. Okay. Then I can write it as g of ti, that is my left hand side, is greater than or equal to g of si on the right hand side, because t minus I is still the same, times plus. So, let us say I also define this as phi. I mean, of course, I am using the same notation, but yeah. So, we can see this point that this is just phi of si, because t minus I is still staying fixed. So, phi of si times this ti minus si. Right? This is exactly like a subgradient function. What is missing? I mean, we cannot still say it is a subgradient, right. So, if this was true, then this is the subgradient, and this is the utility has some properties. Why can't we still say this is a subgradient? We do not know whether the utility is convex, right. We have not proved yet that these utilities are convex, at least in the first coordinate. So, yeah, so we could have said it safely a subgradient if we had this function to be convex functions. Okay, so that is our next task, right. So, you have just done that, defined this, and then you have this structure is a subgradient if G is convex. So, we have not proved it, let us prove it. Okay. Okay, so how should we prove G to be convex? Now, I need the other side. I mean, what do we need to show? If I want to show a function to be convex, what do we need to show? Every chord lies above the function, right? So, how do we show that? So, let us say G function, G is convex, this is what we want to show. So, pick any arbitrary x and y or something, right? So, I mean the general recipe is that pick any. So, G has some domain. So, pick some x and y from the same domain. In this case, that Ti will be that domain, and you show that G of x times lambda plus 1 minus lambda times G of y. This convex combination should be at least as much as G of lambda of x plus 1 minus lambda of y. Okay. That is precisely what we are doing, just that using a different two different numbers xi and zi in Ti, such that, so and because we want to use this y as the convex combination. So, we are just saying this is yeah. So, this is like so let's say z, so xi and zi, so xi plus times zi right. So, yeah, so we are just defining this xi times 1 plus yi as this sorry, this will be zi, and that stuff we have defined as yi. Okay. So, what can we say from what we have proved so far? We have not proved this yet, but what we have proved is that from that condition we know that g of xi. So, we cannot write this one. So, this is something that we will finally show, okay. But we definitely know that if I change from, let us say, t to si, and here for that Ti I am putting this value of xi, and in the case of si we are putting yi, and this exactly becomes that one. And similarly, if I put Ti to be zi and that one to be yi. So, notice that on the right hand side I am always keeping this g of yi. Okay, so this is what we have so far, just replacing the variables here. So, what will be the next step? We want to show that, right. So, that lambda times g of xi plus 1 minus lambda times g of zi, right. So, this is our objective, to show that this one is greater than equal to g of yi, which is the convex combination of these 2 points. So, how can we actually come from here to here? So, multiply with, because this lambda is a non-negative quantity. So, we can multiply both sides without changing the direction of the inequality. Multiply this with lambda, multiply that with 1 minus lambda, add them up. So, the interesting part, what happens here is that because the first term in both these cases were g of yi, that stays, that is just lambda plus 1 minus lambda, which cancels out. You also have this lambda times xi in the first case. So, if you just see that you are multiplying lambda here. So, this will be lambda times xi and 1 minus lambda times zi, and yi will still remain the same, right. So, yi will have multiplier 1, but yi is actually equal to this one, that is how we have chosen yi. So, this entire part actually vanishes, this will be 0, and this part is, we have just expanded it out, that is that one, right. Just a little manipulation, but you finally get this objective. So, now everything falls in place, right. So, I can now clearly see that g is a convex function. So, what we started with, those utilities are convex in the first coordinate. Now, I can safely say that phi function is a subgradient of that, it is a subgradient of the utility. Okay, so, we are still not done. So, what should we do next?
Since f is the subgradient of the convex function, it is non-decreasing.
It is non-decreasing, right. So, that is a lemma we have just seen. Okay. So, we apply these two different lemmas, whatever that lemmas were. The first lemma is saying it is a non-decreasing function. So, we know that this subgradient, which happens to be the allocation function, right. So, what is the subgradient? That is the allocation function, that is non-decreasing. So, the part 1 has been proved, the necessary condition. How do we get the payment function? Anybody except you? Anybody except you? So, how do we get the payment function? The payment function had an integral formula, right. That will be a hint already. So, the last lemma that we saw had this property that if you have a subgradient and you go from one point to another, you look at the difference between these 2 points, that will be equal to the integral of that the subgradient starting from the origin to that destination, right.
Take one point to be 0 and another point to be 3.
Yes. Okay, let's do that. So what we are going to do is we have this g of ti. So we are just using that lemma 4. You are going from, so your there we had, I think, a and b of, I forgot, but yeah, so that the starting point is 0, the other point is any arbitrary ti between in that set capital Ti. Then you have this condition satisfied, because now we have actually shown that this is a convex function and this is its subgradient. So therefore you can write it down and do a little bit of kind of a little bit of algebra, because now I can replace that g value to be the utility. We know the expression for that utility. All you need to do is to reorder and bring that payment function, which happens to be that pi of 0 t minus I. So it does not have to be 0. So if your type set had the minimum value to be negative or something positive, you could have started from that point, and that point would have been the constant value, right. So we are just for simplicity assuming that to be 0. So this is exactly the same part 2. Okay. So what we have actually started with, let me just go back to the statement of the result. So we have shown that if it is DSIC, using only the properties of DSIC, we have shown these two properties, right. So now we will have to show the other way around, because this is if and only if. And I like this part of the proof because it is entirely by pictures. Okay. So the reverse direction is f is given by this non-decreasing function, and we also have the payment formula. So if you look at the payment formula carefully, so I think that is, so now we should look at the payment formula. So far it was not very important, but now it is important. So our payment is pi of ti t minus I, pi 0 t minus I plus ti times fi of ti t minus I. So it is just multiplying the current type with that, and the last part is integrating from 0 to ti fi, let us some running variable x and t minus I dx. Okay. So notice this form, it has a very nice structure, and for this I mean, of course you can do it analytically. Because we are doing graphically, the picture becomes easier if I assume this to be equal to 0. That is how I will be drawing it, but it is not necessary. You can always do a shift of that entire function by this value, and everything will be the same. Okay, so first let us look what happens when we have when the agents are reporting it truthfully, right. So now we will have to say it is DSIC. That means no matter what the other agents are doing, so let us say they are reporting some t minus I, it will not be beneficial for me to report anything apart from ti. So that means I should not be overbidding, I should not be underbidding. In both these cases, my utility should go down, right. And we also know that this allocation function, it is non-decreasing. So for the purpose of the argument will still hold even if you have a discontinuity here, jump like the allocation function in second price auction has. Just to make the picture look nicer, I have taken a continuous growth. Okay, so this is so what this payment is saying is that you have so this payment is taking, so this part is 0. So you are multiplying ti times fi of ti t minus I. So that is ti times fi of ti t minus I. So the entire part here is the first term here, right. And then you are removing the area under this curve, right. So this part is essentially your payment, and your utility, because you are looking at the utility which is the value, the expected value. So this is ti times what is the probability that you will get this minus that payment pi of ti t minus I. So this term we know it already very well, that is the entire rectangle here. Subtract out the payment, then you get this part which is the utility. So this part is the utility, this part is the payment. So remember that we will be comparing with the utility, what happens to the utility. So this is when the agent is truthful. and this is our benchmark. This utility we should not be able to overcome, then it becomes not a truthful mechanism. So, let us first look at when it is overbidding, right. So, when it is overbidding, which part is of this is changing? Of course, your allocation is changing, right. So, this part, let me just use a different color. So, when you are reporting, let us say SI, okay. I should have used another thing because this is the true one, that is the report, but let us assume, yeah, now you understand this. So, by changing the report, what are the things that I can change? I can change the allocation. What else can I change? The payment I can also change, right. This will also be evaluated with respect to SI. This term will still remain the same because this is the intrinsic thing for agent I. It can change the allocation payment, but it cannot change how he values the object. So, because SI changes, this payment will also change. Okay, I am just erasing this part because this is playing no role. Now, notice that because the payment is being calculated by the mechanism designer, everything will change. Wherever you have TI, everything will change, right. So, this is crucial. In the payment term, we will have all these changes. So, you will have SI here, you will have SI here because you have reported SI, and here also you will integrate now up to SI, right. So, now we have assumed that the SI is larger than TI. So, now what is the payment there? SI times this allocation. So, now the allocation function has, so if you evaluate that at here, so this is the value times SI. So, this area of this entire purple rectangle is this first term, and you are also integrating from 0 to SI, right. So, this area under the curve up to the point SI. So, still this entire region is your payment, correct. What is your utility? So, Fi of Si t minus I, so that means you still have the altitude of this of the other rectangle on which you are calculating utility, that is still Fi. So, this point is Fi Si t minus I, right. So, that you are multiplying with Ti. So, this smaller rectangle is the first term in your utility function, right. So, this is the valuation that you are getting. Your valuation will still be multiplied with Ti. So, if I take this, so that is this rectangle here, subtract that out with this strange shaped thing, what remains? So, this common part will get cancelled out, but you will have something. So, now you are having this part which is negative from the utility that you are already getting earlier, right. So, everyone sees that this part will come as, so this minus this whatever is the area of this part. Okay. Everyone clear about this? Okay. So, overbidding does not help. In fact, you can do the very similar thing that if you underbid, then everything. So, this purple line actually moves downwards and you have utility, in that case utility minus this part. So, as if some part of that cliff has been chopped off, right. So, in both these directions it is not beneficial for you to misreport. Okay, so, you can do it analytically if you want to do it just by writing equations, but I think this is giving you a better view of what is actually happening. Okay, so that is it. Yeah, so one corollary, what is it? The allocation rule is in single object allocation is implementable in dominant strategies, because we know that whenever you have a payment, it is implementable in dominant strategies, that F. So, we already have a structure of how you can do this payment, and that will also ensure truthfulness. Okay. So, the Meyerson lemma is now proved. Now, we have a very nice precise structure of how the DSIC mechanism looks like. The other thing that we are left with is the individual rationality, which we are doing on time. Okay, so I just wanted to finish this part. So, maybe after the break we are finishing a little early. If you have any questions, please, we have 4-5 minutes. So, and then after the break, we will look at the individual rationality and we will try to maximize the revenue. Okay. Any questions regarding this proof? Anything?
Could you go back a couple of slides?
Sure. This one?
Like the lemmas were given.
Oh, the lemma is stated. Yeah.
No, we're talking about like
The lemmas of the convex.
measure zero, and what do you mean by measure zero?
Oh, so measure 0. Okay. So yeah, without saying measure, I cannot say. So yeah, so that's exactly. You know this distinction between the real numbers, or the real numbers. The set of real numbers is larger than the set of integers. Let's say. So the way it is saying, so in the space of real numbers, the integers are of measure 0, because as if there are very few number of points, even though there are countably infinite number of integers or rationals, all these are countable, because you can always associate some mapping from the set of natural numbers to them. So the number of the number of points or number of elements that you have in the set of natural numbers 1, 2 up to whatever, that size is the same as in the set of rationals, the set of positive and negative real numbers. I mean the set of not real numbers, the integers. So those are much fewer in number than the real number itself, where you can have rationals, irrationals, everything together. So I mean, I cannot give a more precise definition, but that is the idea that when you are looking at points which are like countably many, so you can have this non-differentiability, and let's say in finite number of points, or even at all possible rational points. Yeah, so between 0 and 1, all the rational numbers that you have, there you have discontinuity, sorry, not discontinuity, that non-differentiability. Still those number of rational numbers are of measure 0 in the entire interval 0 to 1. As if there are almost like no, so when you are looking from the frame of reference of these real numbers, the number of rationals are of 0 measure, that is it. I'm not sure, I mean if that makes sense, is yeah, so yeah, it's not a precise definition, but it's how you can think about. I'll definitely recommend, there is a YouTube channel called Veritasium. So Google for Veritasium, go to I don't know what is the title.
Not
they have
all infinities are same.
Not all infinities are same. Yeah, so it's a very nice explanation of what is uncountably many.